Hello there. Welcome to another video on Enterprise Networking Security and Automation version 7 or ENSA. So on this video, we are going to cover Module 8, which discusses VPN and IPSec concepts. All right. Okay, so what will we learn on this module? So basically, the module covers VPN and IPSec concepts. And at the end of the module, we should be able to explain how VPNs and IPSec are used to secure a site-to-site and a remote access connectivity. So this includes the following topic title and its objectives. So for the VPN technology, we should be able to describe the benefits of a VPN technology. For the types of VPN, describe different types of VPNs, and IPSec explain how the IPSec framework is used to secure a network traffic. Okay, so let's start. We are going to discuss first the VPN technology, or the Virtual Private Network. So basically, VPN is to secure a network traffic between sites and users. Organization uses virtual private networks to create an end-to-end private network connections. So a VPN is a virtual in that it carries information within a private network. But that information is actually transported over the public network, as you see here on the diagram. All right? So a VPN is a private in that the traffic is encrypted to keep the data confidential while it is transported over the public network or the internet. So the figure shows a collection of various types of VPNs managed by an enterprise main site. So the tunnel enables the remote sites, which includes the business partners with Cisco routers, okay, a regional office with a Cisco ASA firewall, and a small home office or SOHO with a Cisco router and a mobile worker using a Cisco AnyConnect. Okay, so these sites here are connected to the main site using a tunnel, which enables remote sites and users to access main site's network resource securely. All right. So what are the benefits of VPNs? So modern VPNs now support encryption features such as the IPSec or the Internet Protocol Security and the SSL or the Secure Socket Layer. So the major benefits of VPNs includes cost savings, security, scalability, and compatibility. So VPNs are commonly deployed in one of the following configurations. So it is either site-to-site or remote access. So a site-to-site VPN is created when a VPN terminating devices, also called as VPN gateways, are pre-configured with information to establish a secure VPN. VPN traffic is only encrypted between these devices, so internal hosts has no knowledge that a VPN is being used. Alright, so next is a site-to-site remote access VPNs. Okay, so a remote access VPN is dynamically created to establish a secure connection between a client and a VPN terminating device. All right. So for example, a remote access SSL VPN is used when you check your banking information online. Okay. Next. Now there are many options available to secure an enterprise traffic. So these solutions vary depending on who is managing the VPN. So VPNs can be managed and deployed as an enterprise VPNs or a service provider VPNs. So when you say enterprise VPNs, These are common solutions for securing an enterprise traffic across the internet. So site-to-site and remote access VPNs are created and managed by the enterprise using the IPSec and SSL VPNs. Now, on the other hand, service provider VPNs created and managed by the provider network. The provider uses the multi-protocol label switching, or the MPLS, at a layer 2 or layer 3 to secure or to create a secure channels between an enterprise sites, effectively segregating the traffic from the customer's traffic. So the figure here, okay, so listed different types of enterprise managed and service provider managed VPN deployments. Okay. Next, so let's talk about the types of VPNs. Okay. So in the previous topic, you learned about the basics of VPN. Here, you will learn about the types of VPN. So VPNs have become the logical solution for remote access connectivity for many reasons. So as shown here on the diagram, the remote access VPNs let remote and mobile users, characterized by a user computer here with a browser and Cisco AnyConnect secure mobility client. Okay, so VPN users here are securely connected to the enterprise by creating an encrypted tunnel in between. Okay, so the remote users can securely replicate their enterprise security access, including email and network applications. So the remote access VPNs also allow contractors and partners to have limited access to the specific servers, web pages, or files as required. Okay, so this means that these users can contribute to the business productivity without compromising the network security. Okay, so next is a client VPN connection. Okay, and a clientless VPN. Okay, so it's either a client-based or clientless VPN connection. So let's start or discuss first the clientless VPN connection. So this is the connection wherein it is secured using a web browser SSL connection. So SSL is mostly used to protect HTTP traffic, okay, or HTTPS, and email protocols such as IMAP or POP3. So for example, HTTPS is actually an HTTP using an SSL tunnel. So the SSL connection is first established, and then data or HTTP data is exchanged over the connection. Okay, so that is using a browser. Now for the client-based VPN connection, okay, VPN client software such as the Cisco AnyConnect here, secure mobility client, must be installed on the remote user's end device. Okay, it could be on a laptop or a palm top or a cell phone. Now, client-based VPN users must initiate the VPN connection using the VPN client and then authenticate to the destination's VPN gateway. Okay, so when the remote users are authenticated, they have access to the corporate files and applications. So the VPN client software encrypts the traffic using the IPSec or SSL and forwards it over the internet to the destination's VPN gateway. So that's how it works. Okay, so the browser based here uses a clientless, okay, VPN through SSL connection, and the roaming users here uses a software called Cisco AnyConnect to connect to the enterprise. All right, next, SSL VPNs. So when a client negotiates an SSL VPN connection with the VPN gateway, it actually connects using TLS, or the Transport Layer Security. So TLS is a newer version of SSL and is sometimes expressed as SSL over TLS. However, both terms are often used interchangeably. Okay? Now, SSL uses the public key infrastructure and digital certificates to authenticate peers. So the type of VPN method implemented is based on the access requirements of the users and organization's IT processes. So the table here compares IPsec and SSL remote access deployments. Okay, so considering the application supported, the authentication strength, all right, so encryption strength, connection complexity, and connection option. Okay, so when we're talking about the application support, so IPsec extensive all IP-based application compared to that of SSL having a limited only web-based applications and file sharing. Okay, so when it comes to authentication strength, okay, so IPsec is strong, so it uses a two-way authentication with a shared keys or digital certificates. Okay, so whereas SSL is moderate one-way or two-way authentication. Okay, so for the encryption strength, so IPsec is strong. The key length is 56 to 256 bits. Whereas for SSL, it's moderate to strong. So key length is at 40 to 256 bits. Connection complexity, well, IPsec medium requires a VPN client installed on the host. Whereas SSL, it just requires a web browser on a host. So any web browsers will do. Okay. And then last is the connection option. So IPsec is limited. Only specific devices with specific configurations can connect. Whereas SSL extensive, any device with a web browser can connect. All right. Next. So types of VPNs, site-to-site IPsec VPNs. Okay, so site-to-site VPNs connect networks across an untrusted network such as the internet. So we are talking about the public network here. Okay, so and hosts sends and receives normal and encrypted TCP/IP traffic through a VPN gateway. So the VPN terminating is typically called a VPN gateway. A VPN gateway device could be a router or a firewall as shown in the figure here. Okay, so which uses a router here and a firewall on the other end. So for example, the Cisco Adaptive Security Appliance or the ASA shown on the right side of this figure, okay, is a standalone firewall device that combines firewall, VPN concentrator, and intrusion prevention functionality into a software image. Okay. Next is the VPN gateway encapsulates and encrypts outbound traffic from a site and sends the traffic through a VPN tunnel to the VPN gateway at the target site. So the receiving VPN gateway strips the headers, decrypts the content, and relays the packet towards the target host inside the private network. So site-to-site VPNs are typically created and secured using an IP security or IPsec. Okay? Next. So GRI over IPsec. So when you say GRI, it's a generic routing encapsulation. This is a non-secure site-to-site VPN tunneling protocol. So I'll show you how to configure GRI on the next video. So a GRI tunnel can encapsulate various network layers as well as the multicast and broadcast traffic. Okay, so GRI does not by default support encryption, and therefore it does not provide a secure VPN tunnel. So it just provides connectivity between the two end nodes. All right, so a GRI packet can be encapsulated into an IPsec packet to forward it securely to the destination VPN gateway. So therefore, routing protocols will not exchange routing information over an IPsec VPN. Okay, so the standard IPsec VPN non-GRI, okay, can create a secure channel for unicast traffic. Okay, so to solve this problem, we can encapsulate routing protocol using a GRI packet, and then encapsulates the GRI packet into an IPsec packet to forward it securely to the destination VPN gateway. So encapsulating GRI into an IPsec allows multicast routing protocol updates to be secured through a VPN. Okay, so we can combine the GRI and the IPsec to provide a secure VPN connectivity. All right, next. So the terms used to describe the encapsulation for GRI over IPsec tunnel are passenger protocol, carrier protocol, and transport protocol. So we are talking about three protocols here combined. Okay, so the passenger protocol, this is an original packet that is to be encapsulated by GRI. So it could be an IPv4 or IPv6 packet, a routing update, and more. Now for the carrier protocol, GRI is a carrier protocol that encapsulates the original passenger packet. And transport protocol, this is the protocol that will actually be used to forward the packet. So this could be either IPv4 or IPv6. Okay, so IP here is for the transport protocol, GRI is the carrier protocol, okay, and this one here, the IP, the TCP, and the data, these are the passenger protocol. Okay, next. So for example, you're gonna have here the branch, okay, and the headquarter. So the branch and the headquarter need to exchange OSPF routing information over the IPsec VPN here. Okay, so GRI over IPsec is used to support the routing protocol traffic over the IPsec VPN. So specifically, the OSPF packets, example passenger protocol, would be encapsulated by GRI or carrier protocol and subsequently encapsulated in an IPsec VPN tunnel. Okay, so with that, with the combinations of GRI and IPsec, for sure we're gonna have a secure VPN connection between a branch and a headquarter. Okay, all right, so the next one is a dynamic multi-point VPNs. Okay, so site-to-site IPsec VPNs and GRI over IPsec are not sufficient when the enterprise adds many more sites. Okay, so the dynamic multi-point VPN is a Cisco software solution for building multiple VPNs in an easy, dynamic, and scalable manner. Okay, so dynamic multi-point VPN or DMVPN is a Cisco software solution for building multiple VPNs in an easy, dynamic, scalable manner. So like other VPN types, DMVPN relies on IPsec to provide secure transport over public networks, such as the internet. Okay? So it uses a hub and spoke configuration to establish a full mesh topology. So when we say hub and spoke, okay, so we have different branches, okay, so serves as the spoke, and maybe the main site serves as the hub. Okay, so spoke sites establish a secure VPN channels with a hub site. Okay, and then each site is configured using a multi-point generic routing encapsulation or mGRI. The mGRI tunnel interface allows a single GRI interface to dynamically support the multiple IPsec tunnels. So therefore, when the new site requires a secure connection, the same configuration on the hub site would support the tunnel. So no additional configuration would be required. Okay, so spoke sites can also obtain information about each other and alternatively build direct tunnels between themselves. So we call it hop or spoke to spoke tunnels. Okay, right. So the next one is the IPsec virtual tunnel interface or the VTI. So the VTI simplifies the configuration process required to support the multiple sites and the remote access. So like the MVPNs, IPsec Virtual Tunnel Interface or VTI simplifies the configuration process required to support multiple sites and remote access. So IPsec VTI configurations are applied to the virtual interface instead of static mapping the IPsec sessions to a physical interface. Okay, so the IPsec VTI is capable of sending and receiving both IP unicast and multicast encrypted traffic. So therefore, routing protocols are automatically supported without having to configure the grid tunnels. That's a good thing about the IPsec VTI. Okay, so the IPsec VTI can be configured between sites or in a hub and spoke topology. Okay. Okay, so the next type of VPN is a service provider MPLS VPNs. So traditional service provider one solutions such as list lines, frame relay, and ATM connections are inherently secure in their designs. Okay, so we've talked about this technology on the previous video. So today, service provider uses the MPLS in their core network. So traffic is forwarded through the MPLS backbone using labels. So traffic is secure because service provider customers cannot see each other's traffic. So MPLS can provide clients with managed VPN solutions. So therefore, securing traffic between client sites is the responsibility of the service provider. So there are two types of MPLS VPN solutions supported by service providers. So these are the Layer 3 MPLS VPN and the Layer 2 MPLS VPN. So as the name implies, they differ and operates on different layers. Okay, so Layer 3 and Layer 2. All right. Now, let's talk about IPsec now. Okay. Now, on this PowerPoint, okay, the official PowerPoint of Cisco, so this includes a video. Okay, so to see this video, you can go ahead and log into your NetHacker account and see this video. All right, so for this video lecture, so I'm going to skip this one. Okay, so let's talk about the IPsec technologies. So IPsec is an IETF standard that defines how a VPN can be secured across IP networks. So IPsec protects and authenticates IP packets between source and destination and provides these essential security functions. IPsec can only protect traffic from layer 4 through layer 7. I'll repeat, IPsec can only protect traffic from layer 4 through layer 7. Okay? So this IPsec technologies provides the following security functions. So you've got confidentiality, integrity, origin authentication, and the Diffie-Hellman. Okay? So when we've talked about confidentiality, it uses encryption algorithms to prevent cyber criminals from reading the packet contents. So that's confidentiality. Okay? Integrity, it uses a hash algorithm or hashing algorithm to ensure that the packets have not been altered between the source and destination or while in transit. Origin authentication uses the IKE protocol to authenticate source and destination. And the Diffie-Hellman is used to secure the key exchange. Okay, so IPsec technologies basically uses a lot of protocols and security measures to ensure that the connection between sites are safe and secure. All right, so we will be covering all those protocols, which ensures IPsec technologies a secure connection. Okay, now, so IPsec is not bound to any specific rules for secure communications. So IPsec can easily integrate new security technologies without updating the IPsec standards. Okay, so IPsec standards or IPsec technologies covers the IPsec protocols, confidentiality, integrity, authentication, and the Diffie-Hellman. Okay, so the currently available technologies are aligned to their specific security function. So the open slots shown in the IPSec framework on this figure, okay, so we have to have a combinations of these choices here. Okay, so to come up with our own combo. Okay, so the open slots shown in the IPSec framework in the figure can be filled with any of the choice that are available for that IPSec function to create a unique security association or SA. Okay, now let's talk about the IPSec protocol first. So the choices for IPSec protocol includes authentication header, okay, or AH, or encapsulation security protocol, ESP. AH authenticates the layer 3 packet, ESP encrypts the layer 3 packet. Alright, so therefore we could have a combination of the both of this, or combinations of these two. Okay, now when we combined AH and ESP, okay, so that is rarely used as this combination will not successfully traverse in a network address translations device or NAT device. Next is confidentiality. Okay, so what do we have in confidentiality? So encryption ensures confidentiality of the layer 3 packet. So choices includes DES, okay, or the data encryption standards, triple DES or 3 DES. You also have the AES or the advanced encryption standard, or the software optimized encryption algorithm, SEAL. So no encryption is also an option. Okay, so you could have a combinations with IPSec and then without encryption. Okay, all right, so the next one is integrity. So integrity ensures that the data arrives unchanged at the destination using a hash algorithm. So this includes the MD5, okay, or the message digest 5, and SHA, which means secure hash algorithm. Okay, the next one is authentication. So IPSec uses an IKE, okay, or the internet key exchange to authenticate the users and devices that can carry out communication independently. So IKE uses several types of authentication, including the plain username and password, okay, so one-time password biometrics, and pre-shared keys or PSKs, which is common, and also it could be a digital certificate using the RSA algorithm or the Rivest Shamir Adelman RSA algorithm. Okay, so for the authentication, the choice is ours. So it's either we use PSK, okay, or the pre-shared keys and the RSA. All right, so the last one is a Diffie-Hellman. So IPSec uses the DH algorithm to provide a public key exchange method for two peers to establish a shared secret key. So there are several different groups to choose from, including DH14, 15, 16, or DH19, 20, 21, and 24. So DH1, 2, and 5 are no longer recommended. Okay? Now, this IPSec technologies would allow the administrator to come up with a great combinations, okay, to have a secure point-to-point or site-to-site connectivity. All right? Okay, so let's have an example of security association here, or SA. Okay, so take a look at the SA example number 1. So IPSec protocol uses AH. Okay, so no confidentiality because encryption it's an option, or you could have without encryption adopted. All right. So integrity uses an MD5, authentication is PSK, Diffie-Hellman is DH16. So Diffie-Hellman is just used to secure the keys. So it doesn't encrypt or provide encryptions for the data. Okay. Now on the Security Association 2 here, okay, so it uses or it prefers ESP, confidentiality uses AES, integrity is SHA, authentication is RSA, and Diffie-Hellman uses DH24. Okay, so an SA is the basic building block of IPSec. So on the next video, I'll show you how to configure an IPSec. Okay, so it's just that on this presentation or video, we are going to cover only the concepts of VPN and IPSec. Now, when establishing a VPN link, the peers must share the same SA. So to negotiate key exchange parameters. So establish a shared key, authenticate each other, and negotiate the encryption parameters. So if you have used an SA with this combination on router 1, okay, just make sure on the other end you have the same combinations or same combo. Okay, so notice that SA example 1 is using without encryption here. That's possible. It is allowed. Okay. Next, the IPSec protocol encapsulation. So choosing the IPSec protocol encapsulation is the first building block of the framework. So you have to choose first on IPSec, okay, confidentiality, integrity, authentication, and the Diffie-Hellman. Okay, so the IPSec encapsulates packets using the AH or the ESP or the Encapsulation Security Protocol. So the AH, it provides data authentication and integrity, but it does not provide data confidentiality or encryption. All right, so all text is transported unencrypted. Okay, next, ESP, it provides confidentiality by performing encryption on the IP packet. ESP provides authentication for the inner IP packet and ESP header. So authentication provides data origin authentication and data integrity. So although both encryption and authentication are optional in ESP, at a minimum, one of them must be selected. Okay? So again, the choice of AH or ESP establishes which other building blocks are available. So AH is appropriate only when confidentiality is not required or permitted. Okay? And ESP provides both confidentiality and authentication. Okay? So again, be careful on building your own combo. Okay? For these security associations, as your SA is the building block of the IPSec. Okay? Next, let's talk about confidentiality. Okay? So confidentiality is achieved by encrypting the data as shown here on the diagram. Okay? So the degree of confidentiality depends on the encryption algorithm and the length of the key used in encryption algorithm. All right? So if someone tries to hack the key through a brute force attack, the number of possibilities to try is a function of the length of that key. So the time to process all possibilities is a function of the computer power of the attacking device. So the shorter the key, the easier it is to break. Okay? So a 64-bit key can take approximately 1 year to break with a relatively sophisticated computer. Okay, can you imagine that? So 64-bit, 1 year. Of course, you're gonna have the most sophisticated computer to do that. Okay, so what if you have 128-bit? Okay, so with 128B or bit, okay, the same machine can take roughly 10 raised to the 19, no? Or that would be 10 quintillion years to decrypt. Okay, so well, the higher the number of bits, Okay, so the secure your data is. All right. Next, continuation. So the encryption algorithm highlighted in the figure are all symmetric key crypto systems. Okay. So DES uses 56-bit key. 3DES uses 3 independent 56-bit. That's why it's called 3DES. Okay. And then the AES offers 3 different key lengths, so 128, 192, and 256 bits. Seal is a stream cipher, which means it encrypts data continuously rather than encrypting blocks of data. So Seal uses 160-bit key. So the higher the number, okay, or the higher the number of bit, so the more secure your data is. So the encryption algorithms in here would merely depend on the administrator. Okay? Okay, so let's have an integrity test here. Okay? When we're talking about data integrity, that means that the data that is received is exactly the same data that was sent. Okay, so potentially data could be intercepted and modified. So for example, on this diagram, okay, so we have here paid to Alex $100, okay, and then the ending hash paid to Jeremy $1,000. Okay, so in here, so assuming that the check is 100, that's written to pay Alex, right? The check is then mailed to Alex, but it is intercepted by a threat actor, maybe. Okay. The threat actor changes the name on the check and make it Jeremy. So when it was sent, it was Alex, but somewhere along the way, all right, it was changed to Jeremy, and that 100 there become 1,000. Okay. So the threat actor changes the name of the check to Jeremy and the amount of the check to $1,000 and attempts to cash it. All right. So depending on the quality of the forgery in the altered check, the attacker could be successful. Okay. So again, when we've talked about integrity, the data that was sent should be the same data that is to be received. Okay. Or the data that is received is exactly the same data that was sent. Okay? There should be no modifications while in transit. Alright. So, because VPN data is transported over the public internet, so a method of proving data integrity is required to guarantee that the content has not been altered while in transit. Okay? So the hash message authentication code, or HMAC, is a data integrity algorithm that guarantees the integrity of the message using the hash value. Okay, so it could be an MD5, okay, which uses 128-bit shared secret key, or the SHA, or the SHA, which uses 160-bit secret key. Okay. So MD5, or the variable length message, and 128-bit shared key are combined and run through the HMAC MD5 hash algorithm. So the output is 128-bit hash. Okay? So we're talking about this. Now for SHA, the variable length message and the 160-bit shared keys are combined and run through the HMAC SHA-1 algorithm, and the output is 160-bit hash. All right, so that's a lot of number of bits. Okay, now let's talk about authentication. So there are two IPSec peer authentications used. Okay, so you've got the pre-shared key, or the PSK, and the RSA. So when conducting business long distance, you must know who is on the other hand of the phone, email or fax. So the same is true for VPN networks. So the device on the other end of the VPN tunnel must be authenticated before the communication path is considered secure. Okay? Now, the figure here highlights the two-peer authentication method. Okay, so which includes the PSK and the RSA. So PSK is less secure and RSA is of course more secure. Now PSK, or the pre-shared key, is combined with other information to form authentication key. So PSKs are easy to configure manually but does not scale well because each IPsec must be configured with a PSK for every other peer with which it communicates. Okay? Now for the RSA, the local device drivers, okay, derives hash and encrypts it with its private key. So the encryption hash is attached to the message and is forwarded to the remote end and acts like signature. So at the remote end, the encrypted hash, the signature is genuine. Each peer must authenticate its opposite peer before the tunnel is considered secure. Okay? So it uses digital certificates to authenticate peers. Alright? Now, let's have the PSK authentication demo here. So the figure shows an example of PSK authentication, or the pre-shared key. So at the local device, okay, the authentication key and the integrity information are sent through a hash algorithm to form a hash for the local peer. We called it hash L. Okay, so one-way authentication is established by sending hash L to the remote device. All right, and then if the remote device can independently create the same hash, the local device is authenticated. So after the remote device authenticates the local device, the authentication process begins in the opposite direction, and all steps are repeated from the remote device to the local device. Alright, so that's PSK authentication. Okay, how about the RSA authentication? Okay, so at the local device, the authentication key and the information, or the identity information, are sent through the hash algorithm to form a hash for a local peer. We call it hash L. Okay, then the hash L is encrypted using the local device private encryption key. This creates a digital signature. All right, now the digital signature and a digital certificate are forwarded to the remote device. Okay, now the public encryption key for decrypting the signature is included in the digital certificate. So the remote device verifies the digital signature by decrypting it using the public encryption key. Okay, so the result is the hash L equals to the decrypted hash L. The local device is authenticated. So after the remote device authenticates the local device, the authentication process begins in the opposite direction, and all steps are repeated from the remote device to the local device. Okay, so you're gonna have a complex authentication here, or complex process, making it a more secure, okay, connectivity. All right, so last one would be the secure key exchange with Diffie-Hellman. Okay, so encryption algorithm requires a symmetric shared secret key to perform encryption and decryption. So how do encrypting and decrypting devices get the shared secret key? That's the question. So the easiest key exchange method is to use a public key exchange method such as Diffie-Hellman, as shown here. Okay, so Diffie-Hellman is used to provide security on the key. Now the DH group you choose must be strong enough and have enough bits to protect the IPsec keys during negotiation. Okay, so for example, DH group 1 is strong enough to support DES and 3DES, but not AES. So another example, if the encryption or authentication algorithms uses 128-bit key the groups 14, 19, 20, and 24 are used. So however, if the encryption or authentication algorithms uses 256-bit key or higher, groups 24, 23, 22, or 21, or use groups 21 or 24. All right. Okay. So the last part of this PowerPoint presentation is the video on the IPSec transport and tunnel mode. Okay. So same thing with the first video. Okay. So to see this video, you can go ahead and log in onto your NetICAD account. Okay. So that ends up our discussion on VPN and IPSec technologies. The configurations will be discussed and presented on the next video. Thank you.